Hello, welcome to today's class. In today's class, we will look in another uninformed search algorithm, which is the bidirectional search. In bidirectional search, we run two different search at the same time. One of the search is in the forward direction, which we performed starting at the initial state, and the second search is in the backward direction, which we start from the goal state. The idea is that if a goal exists, then the two search will meet in the middle. And what we mean by the two search will meet in the middle is that uh, we know that the forward search will maintain its frontier list. Similarly, the backward search will also maintain its fringe list. Now, whenever we find a common element in the two fringe list, that means the intersection of the two fringe list is not a null set, then we can say that we have found a goal. So the test to find whether we have reached a goal or not, that means the goal test, is modified to check whether the two frontier lists intersect or not. Whenever we have a common element in the two lists, it means that the solution has been found. Of course, the first solution we find in this method may not be the most optimal solution. Now let us consider this state space, which is in form of a tree, and in this tree the depth of the shallowest goal node is 4. The goal node is E2 and it is present at a depth of 4, so small d will be equal to 4 because we have only one goal state here, we don't have any other. So this is the shallowest goal node. Now let us perform a breadth first search on this tree, and if we do, by the time we reach the goal state E2, all the remaining red colored nodes has to be preserved in the explored set list. So all the other elements which are red colored has to be stored in the memory in the explored set. And hence the time and space complexity of BFS is big O b to the power d, where b is the branching factor. We have seen why it is big O of b to the power d. We have discussed in details in one of the earlier class also, but also it is evident from here that we need to preserve all the nodes, and we know that if the branching factor is b, then in depth 1 we will have b number of nodes, in depth 2 we will have b square number of nodes, in the depth 3 we will have b to the power 3 total number of nodes, and hence if we add them it would be big O b to the power d. We have discussed that in one of the earlier class. Now let us perform bidirectional search on this same tree. So to perform bidirectional search, we have to perform a forward search, which will start at node A, which was the initial state for the problem, and then we have simultaneously we have to perform a backward search, and for the backward search we will start at the goal state. The goal state was E2. Now let us use breadth first search for each of the two search. So we will perform forward search using BFS, and we will also perform the backward search using BFS algorithm. Now, to start with, the fringe list for the forward search will have the start state A and its explode set will be empty. And for the backward search, the fringe list will be initialized with the start state, which in case of the backward search is the goal state, which is E2. And the explode set will be empty set. Now, let us perform the forward search first. So when we expand node A, it will generate two more nodes. Okay, before performing, we have to perform the goal test. The goal test is to find out whether there is any common element in the two fringe list. The forward search fringe list has only A. The backward search fringe list has only E2. So there is no common element, and hence it means that we have not reached any goal yet. So now let us perform the forward search, and when performing the forward search, we will expand node A to generate two nodes B and C, and these newly generated nodes will be entered into the fringe list, whereas node A will be stored in the explode set. After that, expansion of node A is complete, we will again perform the comparison of the two fringe lists, and still there are no common elements in the two fringe lists. For the forward search fringe list, we have the element B and C, whereas the backward search fringe list has only E2. So there is no common elements, and whenever there is no common elements, it means that we have not reached the goal yet. So now let us perform the backward search, and when we perform the backward search, we will expand node E2, and that will generate a new node O. The newly generated node O will be put into the fringe list, whereas the node E2, which you have expanded just now, will be entered into the explode set. And then we again perform the check whether there is any common element between the two fringe lists, and there is no common element, so we will have to continue our search process. And let us again perform a search on the forward search, and when we perform the next step in the forward search, we will we'll select node B from the fringe list and expand it, and when you expand node B, it will generate the node D and E. So the newly generated node D and E will be entered into the fringe list, and node B will be entered into the explode set. Then again we perform the check whether there is any common element between in the two fringe list. There are no common element, which means the goal has not, we have not reached the goal yet. And then we perform the next step in the backward search, and if we perform the search in the backward search, we will select node O, and we will expand node O to generate two nodes Z and D2. So these two nodes Z and D2, they are entered into the fringe list, whereas node O goes to the explode set. And then we again perform the check between the two fringe lists. No common elements yet, so we continue, and this time let us perform the next step on the forward search, and when we this will select node C for expansion next, and when we expand node C, it will generate two new nodes F and G, and those two new nodes F and G will be entered into the fringe list, whereas node C will be entered into the explored set. And now when we perform the goal test, we will see that there is a common element between the two fringe lists, which was this node Z. And since we find a common element in the fringe list, it means the intersection of the two fringe lists is no longer a null set, and this should and whenever we find a common element, it means that we have reached the goal. And if we look at the forward search and the backward search, the forward search, both of them actually went only up for 2 levels. So forward search stopped at depth 2, and similarly we explored only 2 levels in the backward search. And most of the nodes in the lower depth, they will not be generated. Most of the nodes in depth 3 and depth 4, they will never be expanded. So in general, if this is the depth of the shallowest goal node, then both forward and backward search will meet after each search expands d divided by 2 levels. So in the previous example, we saw that we had d equal to 4, and hence up the exploring 2 levels, the 2 search met. What we mean by the search will meet is that we will find a common element in the fringe list. So in general, if this is the shallowest depth of the shallowest goal node, then both forward and backward search will meet after expanding d divided by 2 levels. And this means that each search in the worst case generates big O b to the power d divided by 2 nodes, because we go only up to d to the power 2 levels. As I already said, in depth 1 I will have only b number of nodes, in depth 2 I will have b square number of nodes, and if I go up to level d divided by 2, I will have b to the power d divided by 2 nodes. So it means so when we say each search in the worst case generates big O b to the power d divided by 2 nodes, it means that the forward search will generate big O b to the power d divided by 2 nodes. I have explained why. And then backward search will also generate big O b to the power d divided by 2 nodes. So the total number of nodes generated will be the sum of these two, big O b to the power d divided by 2 plus big O b to the power d divided by 2, and which actually means this many number of nodes will be generated, which is big O b to the power d divided by 2, and the sum of these two will be equal to this. Thus, the space and time complexity of bidirectional search is big O b to the power d divided by 2. However, the amount of space required can be reduced by half by using iterative deepening for one of the two search. But the frontier from at least one of the search has to be in the memory. Only then we can check whether the two fringe list intersect or not. Now to compare BFS with bidirectional search, let us consider that the branching factor B is equal to 10 and the depth of the shallowest goal node D is equal to 6. Now when we put D equal to 6, it means both forward and backward search will expand nodes up to the depth of D divided by 2, which is 3. So forward search will go up to depth 3, backward search will also go to depth 3 in the backward direction. Let BFS be used for both forward and backward search. If it is so, then forward search will generate 10 plus 100 plus 1000, which is 1110 nodes. Why so? Because we go up to depth 3. In depth 1, there will be 10 number of nodes because branching factor is 10. And then in depth 2, the total number of nodes will be 100. That's 10 into 10. And then in depth 3, the total number of nodes will be 1000. That's because in the previous depth we had 100 nodes, and since the branching factor is 10, it will be 100 into 10, 1000 nodes in depth 3. In the same way, the backward search will also generate 1110 nodes. Hence, in bidirectional search, the total number of nodes that will be generated will be 1110 plus 1110, that is 2220 nodes. However, if we don't use bidirectional search and we use our BFS, that means we are doing BFS but we have only one search, we don't have a forward search and a backward search. In that case, our search will proceed up to depth 6 because that's where our goal node is. So we have to perform BFS up to depth 6. And if we do that, the total number of nodes generated by BFS will be 10 plus 100 plus 1000 plus 10,000 plus 1 lakh plus 10 lakh. And that if we add all these numbers, what we get is 111,110 number of nodes will be generated by BFS. And as you already know how we got these numbers, that's because the branching factor is 10. Hence in depth 1 it will be 10, and in depth 2 it will be 10 into 10, 100. Then in depth 3 it will be 100 into 10, 1000. In depth 4 it will be 1000 into 10, which is 10,000. And depth 5 it will be 10,000 into 10, which is 1 lakh. And in depth 6 it will be 1 lakh into 10, which will be 10 lakhs. So at every level, as we go to the next depth, we have to multiply by 10 because the branching factor is 10. So if we use BFS, then these are the total number of nodes that will be generated. And if we compare the two numbers, it shows the advantage of using bidirectional search. Whereas bidirectional search generates only 2220 nodes, BFS will generate a comparatively large number of nodes. But how can we search backward? So to search backward, we have to start at the goal node and then proceed in the backward direction. If you remember the problems statement, in the problem statement we have the actions for each state in the forward direction. So from a given state, what are the next states we can go to? So now if you want to perform backward search, we have to reverse those actions. And for problems like route finding, it may be easier to do the backward search. It will be easier to reverse that actions, because if we can go from A to B, we can also go from B to A. But it may not be easier for all kind of problems. So to perform backward search, it would require generating the predecessor of a node. And this may not always be easy. Also, what will happen if we have more than one goal node? And the solution is that we will create a new dummy goal node, let's say DZ, and whose immediate predecessors are the actual goal nodes. So with that, I would like to end today's class. We will meet again in the next class. Thank you. Bye.